great to be back here in Boulder with so many, come on in, with so many friendly faces here. My PhD advisor, Scott, here, and also co-advisor, Mike Wiltberger, who many of you know, who used to work in this building, was also my co-advisor on my thesis, and of course doing a postdoc with Mary at Dartmouth. So it's great to be back here. So I want to talk today about some work we've done looking at the radiation belts and the loss processes within the radiation belts. So here's just a quick outline of what I'll talk about today. So for the uninitiated, those of you that don't live in the radiation belts, I'll give a little bit of some background, so hopefully you can orient yourself at least through that part of the talk. Then we'll look at calculating lost timescales from observations, from the Van Allen probe's observations, and then comparing that with previous estimates, similar type of calculations that have been done previously, and then comparing our observed decay timescales with what you would expect from theoretical estimates of what those timescales should be. Okay, so let's jump in here. So for those of you that don't know, these are the radiation belts here, illustrated nicely in this cartoon diagram. So we have the outer radiation belt shown in purple, primarily low and high energy electrons trapped by the Earth's magnetic field in a magnetic bottle configuration, and also low energy ions exist in that same region of space as well. We typically think of the ions as more ring current type population, but overlapping in space with the radiation belt. We have the inner belt shown here in green, consisting primarily of very, very energetic protons and very close to the Earth, and also some sort of lower energy electrons that live down there as well. And then, of course, the slot region in between the two belts that I'll talk a little bit more about today. So where do these particles come from? Well, as many of you know, they ultimately are from the solar wind. So the solar wind field lines are shown here, and they convect over the polar cap, and then reconnect back here on the night side magnetosphere, and those solar wind particles that were on solar wind field lines now become trapped on closed field lines, where they form the plasma sheet in the magnetotail, and then processes, convection, injections, and various processes move those plasma sheet particles in towards the Earth, and they ultimately become energized and trapped into the radiation belt. And of course, it's not just the Earth that has radiation belts. That's what I'll talk about today, are the Earth's radiation belts, but all the other planets that in the solar system that have magnetic fields also have trapped particle populations. Okay, so why do we care? Well, physics is cool. There's this great plasma physics laboratory right out in space, right? And there's a lot of really interesting physics that goes on there, and we can send spacecraft into this region and study the plasma physics in this beautiful natural laboratory. But on a more serious and more practical standpoint, the radiation belts also pose hazards to spacecraft that operate within the radiation belts. And so I won't go into detail about this. A lot of you know about this, but these very energetic particles can cause all kinds of trouble with spacecraft that operate there. And this last bullet here, so we often think about in sort of the inner magnetosphere, global magnetosphere system, we think about the radiation belts as sort of kind of the end product of a lot of processes. The radiation belts don't typically influence other plasma populations in the inner magnetosphere, like the plasmasphere or the ring current. They typically are acted on by other plasmas in ways, but don't typically feed back. But one area where they do feed back into the system is through particle precipitation that many of you study and its impact on the ionosphere and the Earth's upper atmosphere. Okay, so a little bit more about the basics of the radiation belts. So this is a little cartoon movie showing an electron in the Earth's magnetic field. And so a charged particle, an electron here, will execute three types of periodic motion in the presence of a magnetic field like the Earth's. It'll gyrate around the field line. It will also bounce back and forth along the field line between its mirror points in the Earth's upper atmosphere. And then due to the inhomogeneities in the field, it'll gradient and curvature drift azimuthally around the Earth, forming the Earth's radiation belt. So whenever we have periodic motion in a mechanical system like this, we can describe or we can make use of conserved quantities that are called adiabatic invariants. And so associated with each type of periodic motion, the gyro motion, the bounce motion, and the drift motion, we can define these three adiabatic invariants, which are going to be quantities that are roughly conserved, just like momentum conservation, energy conservation. These quantities are going to be conserved so long as, say, the field variations don't vary on timescales faster than the timescales that are shown there. So this use of adiabatic invariants, use of these conserved quantities, really greatly simplifies how we study the radiation belts and how we describe the radiation belts. And so if there were no sort of injections of particles into the radiation belts and there were no processes to remove particles from the radiation belts, they would just do that forever, right? The particles would just remain trapped in this magnetic bottle configuration if they weren't absorbed into the Earth's atmosphere, and they would just execute that motion indefinitely, and they would basically just be these static belts that just sit there. So that's sort of what we call the adiabatic motion of the particles. But of course, we know that the radiation belts are not static. This is a very famous now representation of that very dynamic behavior. So this is actually a paper, or a figure from Mary Hudson's 2014, which I think was adapted from. We say adapted, right? We don't steal things. We adapt from other works. It was adapted from Dan Baker's famous storage ring third radiation belt paper that appeared in Science in 2013. And so that's what you're looking at here. This is kind of the inner belt down here. This is that third belt that appeared, and this is the reformation of the outer belt. So the outer belt has this sort of two-belt structure. So the radiation belts are very dynamic. We all know that. And this is all that non-adiabatic behavior that produces these dynamics. And this figure is actually really nice because it kind of encompasses all of this the main non-adiabatic behavior that we know about. So for example, when you have fluctuations in the field that occur on timescales, sort of on the drift period timescales, you can violate this third adiabatic invariant that produces radial diffusion, inward radial diffusion, which energizes the particles through conservation of the first invariant. That's probably what's producing this sort of enhancement out here. So the belt has dropped out, and probably these particles are radially diffusing inward and becoming energized, producing this sort of second outer belt. We also we know a very important process called local acceleration from gyro resonance. I'll talk a little bit more about this. But this is what happens when you have violation of the first adiabatic invariant. You get a very rapid energization of the fluxes, and that is what's probably occurring out here, where we have this really, really rapid enhancement of the outer belt at this later time. We also have, so those are sort of acceleration or transport processes. We also have loss processes that occur within the radiation belts. Two primary types. One we call magnetopause shadowing. This is where the particles are lost out into the magnetosheath of the solar winds. So what happens here, like for example in this case, you can see that basically the entire outer belt has disappeared. So right here there was a strong compression of the magnetosphere on the day side, a strong shock that interacted with the magnetosphere and pushed the magnetopause very close to the Earth on the day side. And so particles that were once on trapped, azimuthally trapped drift trajectories were now those drift shells were now attached to the magnetopause, and those particles can become very rapidly lost from the system. We have a secondary type of loss process that we know is important, and this is resonant scattering, resonant wave particle interactions that scatter particles out of the radiation belt, and they precipitate them along the field lines down into the Earth's upper atmosphere, which we call precipitation. So you have some, and I'll talk more about this, you have some wave particle interaction that occurs out here, and the particle, it changes its pitch angle and ultimately winds up down in the atmosphere. So this is primarily the interaction that I will describe today.
Hey, before you go away,
sure.
That black line staring at everybody.
Oh yes, that is the location of the plasma pause, I believe. Yes.
That's according to Jerry Goldstein.
Okay, according to another famous Mary student, Jerry Goldstein. Yes, there are many of those floating around here. Yes, that is the plasma pause. Okay, so a little bit more about how all this works, because it'll help you sort of understand what we're doing a little bit later on. So this is a schematic of all of the waves. So there's a whole zoo of waves that we know participate in this wave particle interactions that occur in the radiation belts. So you're looking down on the equatorial plane of the magnetosphere here. The sun is off to the top. So this is the latest incarnation of this figure that appeared in a review paper by Mary and Wen Li that appeared last year. And so just the basic punchline here is that there's all kinds of waves in the inner magnetosphere that we know can do things to the radiation belts. And so how does that work? This is a figure from a radiation belt textbook by Walt, and it's very difficult for you to see, no doubt, because I can barely see it here. But this is, imagine the magnetic field is pointing in this direction, and we're showing here a right-hand circularly polarized Whistler mode wave propagating in this direction. And counter-propagating against that is the electron executing its bounce and gyro motion here. And in the frame of rest in the electron, as it passes and interacts with this wave, it will see wave perturbations in the electric and magnetic field perpendicular to the field. And so if you work out via the Lorentz force equation, those field perturbations, those wave perturbations, will lead to changes in both the parallel and the perpendicular velocity of this particle moving along that way. So this is the wave-particle interaction. So these changes in the velocity will, of course, change the energy. So the energy might go up, it might go down through an interaction like this. And it'll also change the pitch angle, alpha. So the pitch angle is just the angle between this local magnetic field here and the particle velocity vector. So the velocity vector, the particle is bouncing and it's gyrating, so it has parallel and perpendicular velocity. So you change the parallel and perpendicular velocity, you change the pitch angle as well. So one interaction, one electron with one wave, will give it sort of some kick in pitch angle or some kick in energy, and could increase the pitch angle, could decrease the pitch angle. And you get the largest of those types of changes when the wave and the particle have a resonance condition. So this is a resonant wave-particle interaction. Basically, the Doppler shifted frequency of this wave, because it's counter-propagating, matching the cyclotron frequency of the electron. And so you get the largest changes, both up and down, when this resonance condition is satisfied. So that's good for one particle and one wave. What happens? We have lots of particles in radiation belts and lots of waves. So we have many types of these wave-particle interactions, and a little kick in pitch angle in one direction, a little kick in pitch angle in the other direction. That all sort of looks like a random walk when you start to aggregate over many interactions. And so that's like a diffusion process, and we can do a lot with the radiation belts by describing all of these interactions in aggregate in a diffusive framework using the Fokker-Planck diffusion equation. So I've described that, how that works for in energy and pitch angle. This is the whole gory 3D Fokker-Planck diffusion equation that we use in the radiation belt world that you might find in a standard radiation belt textbook. So this sort of looks like a diffusion. You have one time derivative of the distribution function and two spatial derivatives on the right-hand side if you just look at those first two terms. And so this has various terms in it. This first term is the radial diffusion equation that I mentioned before. This represents pitch angle diffusion, so diffusion in the angular coordinate alpha in the pitch angle. And then you have these mixed diffusions, so sort of the cross terms in the matrix, or the off-diagonal terms, and then energy diffusion down here. So you can actually do a lot in the radiation belt world, modeling the radiation belts, by ignoring some of these terms. And actually today what I'm going to talk about, we're actually going to even ignore this radial diffusion term here, and we're just going to look at pitch angle diffusion. Okay, so now you're all experts in the radiation belt physics, so let's start to look at some of the data. So this is same type of format plot that I showed from Mary and Dan's work. This is a L versus time, so we have L on the vertical scale here. This is essentially the radial distance away from the Earth. This is that third adiabatic invariant. And then time is shown along here for about 4 years or so of data. So this is these are 1 MeV electrons measured by NASA's Van Allen probes. And so you can see there's a lot going on here. We have this very, very dynamic outer zone. You see at times you have these very energetic, very strong enhancements of the particles. They can be transported all the way in. This is usually during shock events that we have this type of transport penetrating into the slot region in here, and then sometimes the particles can become trapped down here and forming these sort of transient type interbelt populations. And so one thing that you can immediately note here is that when the particles sort of get into this slot region here, they disappear very, very quickly, right? The particle it's trapped right here, but the loss processes are operating so fast that the fluxes go down very quickly. Whereas if the particles get in just 1 L further earthward, they become trapped. So the loss processes are much weaker here. And so that's what we're going to talk about today is what's leading to that dynamic behavior. Okay, so how do we do that? This is just taking a slice up here through this figure at about L of 4, looking at the flux time series here. And your eye, when you look at this, is immediately drawn to a couple things. We have these very rapid, sort of sharp increases in the flux, these quick acceleration events where the fluxes go up on a couple orders of magnitude in a time scale of, say, 1 day or less. And then very often after these rapid enhancements, you have this kind of slow, gradual decay of the radiation belts, right? And you can see lots of instances of that. You have an enhancement and a sort of a slow decay here. And these slow decays are suggestive of pitch angle diffusion, as I'll talk about in a minute. So we're plotting the data in a logarithmic space, and so whenever you have sort of a straight line feature in a logarithmic space, that suggests that it's an exponential form here to the flux profile in time. And so that's what we're going to look at today, are these sort of exponentially decaying fluxes that we observe very frequently in the radiation belts. Okay, so this is that pitch angle, sorry, a lot of equations, I know. This is that pitch angle diffusion equation that I was showing before, written in a slightly different format. So F here is the phase-space density, or the flux, if you like, what we were looking at on the previous figure. The equatorial pitch angle of the particle. This D term here is the important one. This is the diffusion coefficient, so this governs the rate of diffusion in this formalism. T is just some approximation of the bounce time of the particle along the field line. And then S out here is some arbitrary source term, say maybe radial diffusion or something bringing particles into this. But when we see fluxes decaying exponentially, it strongly suggests that this is the dominant dynamics are pitch angle diffusion, and there's really very weak source probably, or even no source in those types of decays. And why do we say that? So when you look at a PDE like this, you can make some headway in solving it. So you do the usual tricks when you solve PDEs. You assume that the time-dependent portion of the differential equation is separable in the two variables here, so alpha and time. So we have these two, the dependence is all the angular dependence is in one function, and all the time dependence is in the other function h. And so if you assume that time dependence is an exponential, you can sort of factors out, and you get this ordinary differential equation down here, just in the angular coordinate, just in the pitch angle coordinate. And so the way I've written it here, this is, I've written it in sort of a suggestive way, where on the left-hand side, you basically have a differential operator acting on this function g, and on the right, you have a constant times that function g. Right? So this looks like a matrix eigenvalue problem, right? You have matrix times function equals number times function. And so this is actually a very well-studied type of equation in applied math type world. It's called a Sturm-Liouville type equation, and it has very nice properties. And one of the nice properties is that all of the eigenvalues for pretty relaxed assumptions on this function g, all these eigenvalues, tau or 1 over tau, are real and they're ordered. And what happens is, because they're ordered, you have some sort of transient behavior initially, but then the solution all settles down into the lowest order eigenmode. So the smallest eigenmode, the smallest eigenvalue. So the smallest eigenvalue is 1 over tau, so basically the longest decay time. And then the whole distribution, the whole function g, basically decays with that one eigenvalue. And so that's why we think when we see profiles that look like I was showing in the data, where we have the flux sort of decaying exponentially, that it strongly suggests that we're looking at pitch angle diffusion.
Did I ask you a question?
Yeah.
So if the particles are being lost, it suggests that something was pumping up that diffusion coefficient.
That's right.
And so, but you're treating it as constant here.
Oh.
So there's an assumption that it's constant over the time scale of the decay. Is that what you're?
Constant in time?
Time, right.
Yes. Yeah. And it's probably not, but as you can see from lots of modeling work, that does a really reasonable job of describing the dynamics. Yep. So it's these types of losses that we're going to talk about today. And so these particles, because they're decaying away, right, the particles are going somewhere, and they're ultimately being scattered into the Earth's upper atmosphere and the ionosphere as precipitation. Okay, so back to this picture. So we devised this way to go through time series like this with an automated algorithm and identify these straight line decays, these exponential decays, fit an exponential function, and to calculate the decay time constant tau. So this is not anything that we invented. This is based on work by Nigel Meredith and adapted in this paper by Sylvie Bank. And so we've kind of tailored it to the Van Allen probes data set, and I'm showing an example of it applied to this time series here. And the numbers here are the decay time scales in days. And you can find some examples where it hasn't gone in and fit all of them, but we wanted to sort of remove the human from the equation and let the computer go off and calculate these things, which is sometimes a good thing. So
how do you bin the data
Okay.
to choose a time interval such as you have a new fold of the time?
Yeah, so there's a whole bunch of criteria that we have for this algorithm. One is that we require that the decay be longer than 5 days. Is that kind of what you're asking?
Yeah.
We certainly, like these data right here are binned in time. They're daily averages.
But then you have to cut it off.
Right. So we basically we follow it until we have a goodness of fit criteria on the fit, like a R squared and a some other goodness of fit criteria. And basically we take an interval like this and we fit until the goodness of fit R squared value goes below some threshold. As like if you try to fit like from here to here, it'll start to get really wonky. And so that allows us to sort of stop the fitting process by looking at the goodness of fit. Okay, so I'm just showing here one energy channel and one L value, but of course, the Van Allen probes sample this entire radiation belt region, and not just at this energy. We have many, many energy channels across the radiation belt region. So the idea is we'll throw this algorithm at all of the data and see what we get. And this is what we get. So we're going to do a lot of comparisons with this figure throughout the rest of the talk. So let me just take a minute to explain it. And now the L coordinate, the radial coordinate, is plotted along this axis, and then energy is plotted here. So we have at each L bin and each energy bin, we go in and fit the time series and have some number of decays events, 10 decay events, 100 decay events. And then in each bin, we take the mean of all those decay time constants, and that's what produces this figure here. So this is sort of the mean decay time or the mean lifetime of particles in each energy in L bin. Okay, so your eye is immediately drawn to several features in this figure. The first is this big blob of red, probably down here at lower L. And so you can see down here in the inner zone, these mean decay times are very long. Like if you look here at 1 MeV, at the heart of the inner belts, it's sort of on the order of 100 or 200 days or so. And so that's what I was alluding to before in that L versus time plot, where we saw those electrons become trapped at the inner belt and they stay there for a very long time. So whatever is producing the scattering is doing so at a on a very, very slow time scale. And if you contrast that, as you move out in L, you pick up this very dark black region here. So when it's black, it's below the bottom of the color scale here. So these are very, very rapid decays that occur in here. And so this is the slot region here. We know the slot region is energy dependent because of these energy dependent scattering processes. And so when particles get into this region, they're rapidly scattered out of the system. And we'll see what exactly is doing that in a moment. And then as you move out here to higher L and higher energy, the decay timescales start to increase again a little bit, but certainly don't reach the same levels that you see down here in the inner belt. Okay, so I'm just going to skip through this. Those are just a little bit more about the goodness of fit criteria and things that we use. I can come back to that at the end. Okay, so the first thing, so now we have this database of lots of decay events from the Van Allen probes data. As I mentioned, Nigel Meredith and these other papers have done a similar thing using older data sets. So we want to go through and just make sure that what we're doing looks similar to what has been done in the past. Okay, so this figure is now, again, plotted versus L. Now the decay time is on this scale, and now I'm just plotting at a fixed energy. So basically a slice to that color figure we were just looking at a fixed energy. The gray trace here is what we've obtained from Van Allen probes. And then in the different colors, I'm showing various different previous estimates. So the bank work that I mentioned used a couple spacecraft that were in LEO, in low Earth orbit. That's shown in black. The red is from the Meredith paper, which used data from the CREST spacecraft, which was sort of the previous big radiation belt mission that we had back in the early 90s. There's a purple trace here from Vampola, which was this OV33 spacecraft. That's shown in purple here. And then there's one orange point there from a work by Secchi et al., also using the CREST data. And so you can see there's a couple things here. Down here in the inner belts, there's really nothing else to compare with at this energy. And this is sort of one of the really feathers in our cap from Van Allen probe, is that this is really the first time that we've made really, really clean measurements of the electrons in the inner belt. So we have, with the MAGICE instrument on Van Allen probes, we have an ability to calculate what the contamination is, because when we're in the inner zone, the very energetic protons can wreak havoc with your sensor. And so we have devised a way with the MAGICE instrument to remove that contamination. So we're very confident in the signals that we're measuring in the inner belt. And most previous estimates have been highly suspect, I would say, with their measurements there in the inner zone. So there's not much to compare with down here, but certainly we get a nice agreement. The purple and the black trace is under there as well, at least up to there. So this really steep gradient in the decay timescale through the slot region is really nicely reproduced in the Van Poel and the bank work. And I'm showing 1 sigma error bars here on the MAGICE. And as you move out here into the outer belt, you can see that generally there's pretty good agreement with the prior estimates. We have to remember that you can see the years on here. So all of these estimates were made during different parts of the solar cycle, different portions of the solar cycle, different solar cycles themselves. But from a physics standpoint, we would generally expect the processes that produce these pitch angle diffusion, these decays, to be essentially the same from solar cycle to solar cycle. And so it's reassuring, at least at this energy, that we're doing a pretty good job. This is the one you were just looking at. Now I've just taken some other energy channels and shown them here. This is 750 keV. Again, reasonable agreement. There's some disagreement in here. We actually think that this might be some contamination issues with some of the earlier measurements, and I can talk about that at the end. Out here at the higher energies, sort of 1 and 2, 3 MeV, pretty good agreement. We don't have any data in the inner zone here. That's another thing we've observed at during the Van Allen probes era. Basically, 1 MeV electrons are the highest energy electrons that we've observed in the inner zone during Van Allen probes, so we don't unfortunately have any measurements at higher energy there. This pink trace here is from another Nigel Meredith work where he used the Sampex 2 to 6 MeV channel, so it's a pretty wide channel, but at least sort of they're starting to agree in the overlap region. Bottom row is what you were just looking at. Top row now here is at lower energies. One thing I'll draw your attention to here at, say, 50 keV, this is actually kind of below what we typically think of as radiation belt energies. But there's basically nothing else to compare with. And so we got a lot of flack from the GRL reviewer saying, you can't possibly have gone through and found nothing to compare with. And, I kept saying, I did very extensive literature search. There really isn't anything else out there in a lot of these comparisons, which was a little surprising to us. But so there's this little pink trace out here. This is from a work by Sue, a spacecraft called Scatha. Reasonable agreement there. A little bit higher energy, say 200 keV. We have this work from West, the green. Looks very good. You can see these black traces here from the bank work right a little bit higher in all these cases. So we think that there's some contamination. We've talked with her about this. And there might be some issues there with that instrument that was used there. But nevertheless, certainly, I think we have pretty reasonable agreement with some of the prior work. So bottom line, I think we haven't done anything crazy. I think what we've got here is a pretty good database of particle lifetimes from the Van Allen probes. Okay. All right, so that's the observations. So now what we want to do is we want to take those observed decay timescales and compare that with what we'd expect from scattering due to various scattering processes to see if it all kind of matches up. All right, back to this equation one more time. I promise this will be it. Okay, so what we want to do here is we want this diffusion coefficient, as Bill alluded to, is what governs the rate of scattering, right? It governs how quickly these particles are scattered out of the system. And so you can go through and you can solve this full ODE to compute the eigenvalue tau, which is what we're after, by specifying the diffusion coefficient. There's actually a pretty good approximation that works here. So this was derived by Jay Albert and Yuri Spritz in their 2009 paper. Not an exact solution, but a pretty reasonable estimate. So the particle lifetime, the decay time scale basically goes like 1 over the diffusion coefficient. You integrate it from the loss cone angle up to 90 degrees. So the idea now is that we take our favorite scattering mechanism, say plasmaspheric His waves, which is what's shown here. We compute the diffusion coefficient, d alpha alpha, for that scattering mechanism, and then run it through this formula, and that tells us what the decay timescale should be for scattering via His waves in this case. But we know there's, like I showed on that schematic, there's lots of waves that do this scattering. So we're going to include many processes. I should mention that this is all sort of done in this quasi-linear diffusive framework. And there's been a lot of work recently maybe suggesting that quasi-linear diffusion isn't the most appropriate in some instances. But nevertheless, it seems to do a pretty good job describing the radiation belts. So we will proceed in this quasi-linear diffusion framework. Okay, so these are diffusion coefficients just due to His waves. So how do we do this? So we have some empirical database of the His wave amplitudes, say. So this is His wave amplitude plotted versus L. So these are just from statistical observations from Van Allen probes and other data sets where they've basically found all the His waves, binned them up in terms of geomagnetic activity, which I'm showing here in different color or in different traces, and L. And you get profiles that look like this. So as activity goes up, the His wave amplitudes go up. But they sort of peak in sort of this 3 to 4 range. And so we take those wave parameters that we know from statistics, and we use those to compute the diffusion coefficients in the usual way. So the His wave scattering is pretty weak down here at L of 1.5. The scattering starts to increase here at the higher energies. And then as you move up in L, the scattering becomes more important at the lower energies. And these are all plotted versus equatorial pitch angle. Okay, so this is the one we were just looking at. So His waves are important for scattering radiation belt electrons. One of a very important process, certainly in the inner, when you get close to the Earth, is Coulomb scattering. And so this is where particles are bouncing back and forth along their field line, and they at the mirror points, if the mirror points are at low enough altitude in the Earth's upper atmosphere, they will start to interact with atmospheric neutrals and atmospheric ionic species. And they will have Coulomb collisions with those particles, and that will remove them from the system. This is what produces the precipitation, essentially. And so Coulomb scattering, particularly very close to the Earth, is an important process. This region of enhanced, basically infinite diffusion coefficient, that vertical line here is basically the loss cone angle. So once particles enter the loss cone, they're lost from the system via Coulomb collisions. The loss cone angle decreases as you move up in L. But even at L5, Coulomb scattering is not insignificant at those altitudes. So that's important to include, as you'll see. Another important process is scattering via VLF transmitter waves. So on the surface of the Earth, there are these very high-powered VLF radio wave transmitters that send out very high-powered radio waves that communicate with Navy submarines throughout the world, so various navies operate these transmitters. And so these transmitters can penetrate, the radio waves can penetrate into the ocean to send signals to submarines. They also bounce around in the Earth ionosphere waveguide, and they can leak out through the ionosphere into the near-Earth space. And when they do, they propagate in the Whistler mode. And so just like Whistler mode His and Whistler mode chorus, they can resonate with electrons and scatter them in the radiation belts. This scattering is important at low L because that's essentially where these transmitters are located on the surface of the Earth. When the waves leave Earth and propagate out into space, it's primarily at lower L values, so we don't really have an effect out here at higher L value. But this, we've known for some time that this is an important process. We have observations of suggesting that this does indeed scatter particles out of the radiation belts. And as many of you know, electromagnetic ion cyclotron waves are also an important scattering process to include, most important at the higher energies and at the higher L values. This is where you have a lot of EMIC wave activity, and due to the resonance condition and how it works, they typically only resonate with higher energy electrons. Okay, so that's all that we're going to talk about in terms of the diffusion coefficients. And now basically the idea is you sum them all up and see what the scattering rates are and what that produces in terms of the particle lifetimes. Okay, so here we go. This over here is the observational database that I described before, our mean lifetimes from the Van Allen probes. And then this first comparison here is just with scattering from plasmaspheric His. So we've taken the diffusion coefficient from plasmaspheric His and integrated it and computed the lifetime values here. Okay, so from a qualitative perspective, you can see sort of the shape of these two profiles looks very similar. The morphological structure looks similar. You have long lifetimes in the inner zone, you have a slot region right here, and then you have these sort of higher lifetimes out here at higher L and higher energy, right? So this is nothing new, right? This is Lyons and Thor in 1973. The role of plasmaspheric His in producing the slot region and so forth. So I would say that qualitatively, this structure that you see here is largely due to plasmaspheric HISS, something we've known for a long time. But there's some very important differences. The color scales are different here. The one on the right goes up to 1,000 days, so much higher. So something is really going on here in the inner belt to remove these particles. Plasmaspheric HISS just isn't doing it down there, nor so at higher energy in higher L. All right, so let's start to include some of the other scattering mechanisms I described. Now we're including HISS and the VLF transmitters. So these ground-based transmitters that I said were important in the inner zone. And so you can see here, if you compare these two, you can see it has pretty significantly reduced the particle lifetimes here in the inner belt, which we would expect. And as you'll see in a moment, it has also produced this little local minima there that actually exists in the observers as well, which I'll show you a little bit more in a moment. Okay, so now HISS, VLF, and now Coulomb scattering. As I mentioned, Coulomb scattering, very important near the Earth. So you can see if you look really, really close to the Earth here, where sort of the Earth's upper atmosphere and ionosphere overlap with the radiation belts, you can see that this whole region has basically been scrubbed out, right, from this. So the Coulomb collisions are producing this sort of secondary peak here in the inner zone. So we have this peak lifetime, a little local minima there. So this is really where the transmitters are really taking over, and then another little local maximum there. But you can see here in the outer zone, basically nothing has changed. Then we include the EMIC waves, which, as I mentioned, we expect those to be important for the higher energy and the higher L. And you can see they have a dramatic impact up in this corner if you compare these two. Okay, so now if you compare far right with far left, I would say we're at least qualitatively getting something that looks a lot like the observations. The slot region, the reduced lifetimes out here, and the long lifetimes in the inner zone. But quantitatively, we're still pretty far off, and this is kind of like our best guess as to what's going on. Yep, Maria.
Did you look at chorus at high L shells?
Chorus at high L shells, yes. So
High energies?
we have not included chorus waves. So chorus waves are also important. So there's a reason why we haven't done that. So in the inner magnetosphere, wherever the plasmasphere goes, that sort of defines the boundary between where HISS waves are acting and where chorus waves. So HISS waves occur in the plasmasphere, and chorus waves basically occur outside the plasmasphere. And in our observational database, it turned out it was like really hard to separate these decays with respect to where the plasma pause was, because you can imagine, say at L04, I have something that's decaying, and the plasmasphere might move over that boundary during the course of the decay, which is a whole other subject. But by and large, what you're looking at in our observations are mostly within the plasmasphere. So I've gone through and tried to separate it out, and it's especially below L5 or so, everything that you're looking at in our observations is by and large inside the plasmasphere. So that's why we didn't include the chorus wave scattering. But certainly it is also going to be important at higher L and higher energy. Okay. So qualitatively, we look correct. Yeah, another question? Sorry. Qualitatively, at least, we look correct, but quantitatively, a lot going on. Still to be done. Okay. I just want to quickly go through and show you some slices now in a line plot format through these two figures. So this is at the lowest energy that we have, 32 keV. The pink and the purple are theoretical estimates. So those are from this figure over here where we have all the scattering processes incorporated. The pink is for Kp equals 5, so a high activity case, and the purple is for Kp equals 0, so a low activity case. And much like the plasmasphere issue, it's actually hard to organize these observed decays with respect to activity. They generally occur during quiet time, so you have a storm, it increases the flux, and then the storm dies away, and then the fluxes start to slowly decay. So generally, what you're looking at in the observations is for a lowish Kp value. So we've just sort of indicated these two. I should have mentioned that this top row was done at Kp equals 2, which is kind of the mean Kp. But this gives you an idea of sort of the bound range and activity levels. Okay, so in the theoretical profiles, I mentioned this little local minima there. So that local minimum there is due to the action of the VLF transmitters. So this is the the anthropogenic impact on the radiation belts. And there it is in the observations. So yeah, it's very, there's a lot of, it's not outside of the error bars very much, but there is no doubt a little dip there in the observed lifetime profiles as well. And it's at essentially exactly the same L value as where you see it from the theory. And so that's a really good smoking gun because we know where these transmitters are on Earth, and so we know how they propagate out into space. And so it should show up in the observations at precisely the same location, and it does. Now, of course, as I mentioned, there's basically an order of magnitude difference between what we see from the theory and what we see in the observations. And I'll come back to that in a little bit. Now, as you can see, if you look at up here, the location of where that local minima is changes. It moves to lower L as you move up in energy, and that's due to the cyclotron resonance condition and how it works. So we should see some signature of that in the observations, and indeed we do. There's a little local minima in the observed profiles, and then as you increase energy, it starts to move slightly earthward, and you can see a little hint of that right up in there as well. So I think this is pretty strong evidence that in our statistical lifetime observations, we have pretty strong evidence of the human impact on the radiation belts. Okay, so moving up in energy now, say 350 keV. This you can see here we're doing a pretty good job even quantitatively here at this energy where the two activity traces from the theory sort of bound what we see in the observations, which is what you would like to see. The slope of the steep gradient here is largely consistent between the two, but again in the inner zone we're really missing something in our calculations. Now moving up in energy, particularly as you get into the multi-MeV energy range, you can see here that kind of in this region here the two profiles bound the observed, but as you move to higher L, the trend starts to kind of deviate a little bit. And so probably what's going on is the EMIC wave scattering that we're including is probably a little bit too strong. This is actually really, Mary and Maria and I have talked about this. It's really tricky to get this kind of scattering right, especially in a statistical sense. But nevertheless, it certainly is needed, and probably chorus scattering is important too for kind of reproducing what we see in the observations.
Can I ask,
Yeah.
in your EMIC model, do you assume some longitude range that the particles
Yes.
interact with EMIC with?
Right, we basically assume that it's some fraction of the drift orbit, and I can't remember, maybe 10%, 25%, I can't remember. But yes, we did something that other people have done.
And you can, of course, vary then its effectiveness.
Yeah, exactly. In any of this business, there's all kinds of knobs to turn, right? But at least we just wanted to see that, all of these things that we believe are important, is it able to reproduce the observed? Because people often just, take these diffusion coefficients and run the model, and no one has ever really looked at, how well these diffusion coefficients compare with what actually the particles are telling you about the scattering processes. So that was kind of one of the goals of this study. Okay, so I've been mentioning this VLF transmitter thing just because I think it's cool. So the VLF transmitter thing has been around for a while, actually. So there's lots of people in this world who would love to remove the radiation belts entirely from space. People that have lots of money invested in satellites, like commercial companies or militaries around the world, because the radiation belts pose a space weather hazard. And so there's actually been a lot of discussion and work done to try to see if we can artificially remove the radiation belts using mechanisms like this. So there's actually a spacecraft flying around in space right now called DSX, which is a US Air Force mission, flying not certainly high-powered transmitters like we have on the ground, but flying sort of miniature versions of those and shooting off radio waves and seeing if it'll scatter the particles out of the radiation belts. But we saw this VLF transmitter effect in our statistical database of the lifetimes, and we thought, well, if it's there in the statistics, it should certainly be there in the raw observations. And lo and behold, it actually is in the observations, and it's kind of been staring us in the face all the time. So these are now just the raw fluxes from Van Allen probes. If you look at this one, it's 75 keV electrons. So we're just looking at the inner zone, say L of 3 and less, and you can see here that we have this sort of kind of stripy thing there, and you can see there's a little local minima there. Maybe you can see it, maybe you can't. I assure you it's there. And then sort of a secondary peak in the inner belt there, right? So we're referring to this as sort of a bifurcation in the inner belt, where we have sort of these two inner belt populations that are separated by this local minimum and the fluxes that is due to these VLF transmitters. So Dan Baker in 2013 told us that there are 3 radiation belts, right? So now I'm telling you that there are actually 4. So down here we have a bifurcated inner zone, in addition to, at times, a bifurcated outer zone. These are just time averages of these fluxes shown here, just so you can see those little local minima are there. They're not huge, but they do also, as I mentioned before, move earthward with increasing energy, which is exactly what you would expect for cyclotron resonance with the VLF transmitters. Okay, so let me just say a few words here at the end. So I hope I've been able to convince you that we have a nice database of decay timescales in the Earth's radiation belts obtained from Van Allen probes. We think they agree quantitatively well with past work in this area. We've identified, if you go and look at the paper that we just published in GRL, that a lot of these differences are likely due to instrumental effects in some of the previous measurements, which is always a difficult topic to broach, but we've done it nevertheless. I haven't talked about the 2-stage decays. I can at the end. Quantitatively, at least the gross morphology, I think, is there and reproduced by the scattering processes that we know are important or we think are important in the radiation belt. The overall structure due to the His wave scattering, the influence of the VLF transmitter waves at low energy and low L, and the EMIC wave influence at high energy and high L. But again, emphasizing that these are 2 vastly different color scales here. And so what's going on at low L? What are we missing? So let me just say a couple words about that. So there's some potential explanations for what we haven't done right at low L. There's another population of waves that we know is important in the radiation belts. And so lightning, when it occurs in thunderstorms on the surface of the Earth, also propagates VLF waves out into space, much the same way. And for much the same reasons, these waves can also scatter electrons, and we have examples of this as well. Our incorporation of lightning into all those calculations was sort of done in an ad hoc way. The His wave database that we used kind of included the lightning. They didn't do a good job separating it, and so we'd like to do a better job explicitly incorporating the lightning-generated Whistler waves. All this business with the VLF transmitter waves, and you have to make various assumptions about those waves, probably could use some improvements, and actually people are working on this basically even before we published this work. These 2 papers appeared from Nigel Meredith's group, someone that works with him, Ross, in 2019. And what you're looking at here, the gray are those are our calculations, our theoretical calculations that I showed you before, and the black here is our observational calculation. And the red here is their improved estimate of scattering from VLF transmitters. And so you can see they're a little bit lower than ours, agreeing a little bit better with the observations, but still not getting all the way down to where the observations say we are. So what else? So for those of you that know Jay Albert, every time I show these results last year, he was always, you've got to include Coulomb energy drag. So this is where the electrons, in addition to Coulomb scattering in the ionosphere, they also ionize neutrals in the atmosphere, and they lose energy when they do that. And this is a process that we have not included. It's kind of difficult to include. But he was telling me, you've got to include it. And I kept saying, why? And he says, well, I have a paper coming out soon, and you'll see. And so he did just publish his paper this year. And there's a lot going on here. I don't want to get into it. But the black dots are observed, and the grays, again, are our theory. And all the red traces are essentially what he's done, incorporating this Coulomb energy drag. And you can see his color traces are a lot closer to the observed. He's also done a whole bunch of other things here, too. He's done a whole rework of lightning. He's done a whole rework of the VLF transmitter. It's really a comprehensive work that they've done. So I think sort of everything is kind of converging onto the right answer, but more remains to be seen. So
What's the grain in those figures, or I should just look at this paper?
yeah, I don't remember. I didn't put it on here, probably because I don't think I could make sense of it originally.
Yeah, okay, I'll just look at this paper.
But there's just various types of assumptions about VLF transmitters, whether or not they're propagating in a ducted mode or an unducted mode, various assumptions about lightning and all kinds of different things. But yeah, so I think that's all I wanted to say. So thank you very much. And I should mention, so a number of people have contributed to this work beyond the co-authors, and so they're listed there. And as I mentioned, after many battles with the referees, we finally were able to publish this in GRL and 2 papers that appeared just last month. So go check it out if you're interested.
So how about the two-stage decay? So sometimes instead of a single exponential decay,
Yeah.
you see 2, and it's
All right.
been suggested 2 wave modes.
Right, so 2 eigenmodes essentially. I have too many. This is like what I learned from Scott when I was his PhD student. Lots of backup charts. Okay.
Yeah, there you have it.
Yeah. Okay. So there's been a lot of reports of these things called of what they're calling two-stage decays. And so basically, what you have is you have the enhancement, and then you have decay at one time scale, and decay at a second time scale later on, right? And so this has been observed a lot, and we've heard about it a lot. And so there have been a number of suggestions. Maybe it's 2 eigenmodes, decay in the lowest 2 eigenmodes instead of the lowest eigenmode. Actually, we think that it's really a lot simpler. So almost all of those reports of two-stage decays all came from integral flux measurements. So and what we've done here is we've taken the MAGI's data and we've computed integral flux above half an MeV and looked at this. But now what I'm showing down here is the differential fluxes for the same energy range. And so what you can see here is that fast initial decay is governed by the lower energy electrons, and that slow. So it's basically the thing that I was describing today, the really rapid, the very dramatic change in particle decay timescales as a function of energy. And so if you go back, and actually Jean-François Ripoll suggested this in one of his papers where they were looking at in integral flux measurements. He was saying that it was likely this situation, but they didn't have the measurements to be able to show it. And so we showed it pretty explicitly in the paper, and the negative reviewer said, "Oh, that's obvious. Everyone knew that." But that's how these things go.
Oh, okay. It sounds to me as if it would be nice if you could convince the Navy to turn off those things.
Yeah. Good luck with that. Maybe you have friends in higher places than I do. But actually, no, this is a very interesting suggestion because it actually has been done before. So the Navy won't tell you that they're going to turn them off because that'd be a national security thing. But they do go down from time to time for maintenance, as you can imagine. Like, things break. And so there have been time intervals where the transmitters have been turned off. And we've looked at that, and we didn't see the exact signature that we would have expected to see. Part of the problem is that there's about 20 of these transmitters around the world. There's about 3 or 4 that are really, really high powered, and that are probably the ones that are dominating this. That Ross paper that I mentioned actually went in and looked at all 19 transmitters and studied each one in isolation. So you'd really want to turn off like the 3 or 4 most powerful ones. And no one's done that yet. So
Another thing is what would ought to be the dependence of the scattering parameters on the power that's being transmitted?
So it's definitely the higher power, the more wave power you get in space generally, and all things being equal, and then the more scatter you get. So if you put a bunch more of these transmitters, the high powered ones, around the Earth, you could probably reduce the radiation belt flux pretty significantly, at least in the inner zone at these energies.
You would not only reduce it for relatively low energy electrons.
Mm-hmm. Sorry,
You would only reduce it for relatively low, like electrons with maybe less than 10 kilovolts.
Yeah, that's kind of what we're showing here, right? To get them to resonate with the higher energy electrons, you have to play some games with the densities and so forth, but that, because you're inside the plasmasphere, that doesn't change that much. So yeah, it's predominantly the lower energy electrons that get scattered. Maria.
Well, I also had a question about the
Uh-huh.
biospheres. So how does the bifurcation zone work? Why does the location depend on the particle energy?
Why does the location depend on the particle energy?
Yeah.
That's just the cyclotron resonance condition, and how it basically is predominantly the magnetic field dependence and the density dependence. So if you just take some simple model, like a dipole field model, and some simple like Scheele or some plasmaspheric radial profile model of plasma density, you can work out how the cyclotron resonance. Actually, that was in the figure. I never mentioned it. Oh boy. Here we go. We gotta go a long way backwards.
I noticed that.
This thing, this is basically, sorry, I didn't mention this, this L to the 6 curve, that's basically what you expect for cyclotron resonance, is that dependence. And so you can see it matches up pretty nicely with that energy dependence.
Yeah, so back to the time dependence, the diffusion
Yeah.
coefficient. I mean,
Yeah.
these are like 100 days.
Yeah, not always. Yeah, so I agree. This has always kind of been a head scratcher, but so with the very long decays, like the 100-day decays in the inner zone. So really, it's Coulomb collisions and probably lightning and VLF waves, and those are kind of always there, right? Those don't really vary with geomagnetic activity. You know, Coulomb collisions certainly not, and VLF transmitter waves are always on, and lightning's always happening, right? So those are quasi-steady sort of behaviors, and that's really for the long decays in the inner zone. That's really what scatters those particles. But certainly in the slot region, where it's His, you know, His comes and goes. It's kind of always there, but activity goes up, His goes up, and it moves around. You know, Dave Malaspina, who many of you know, has shown that sort of His kind of tracks with the location of the plasma-pulse boundary, and why it produces a steady exponential decay when things are moving around like that. It's bothered me too, but you see it in the data, and it's what the theory suggests. So, yeah, Gong.
I just wondering that, do you know the relative contribution from VLF transmitter loss and versus lightning loss? I would imagine that VLF transmitter mostly through over the ocean, and the lightning mostly
Yeah,
through land.
right.
Do you see the difference between these? And also lightning should have some kind of seasonal variation.
Yeah, absolutely. So this is, we've looked at for these kind of signatures a lot, particularly the seasonal variation in lightning. The continental stuff is tough because, right, the Earth is rotating essentially underneath the radiation belt, right? And so it's, and you know, these observations, you know, these were daily average observations, and so teasing out a signal like that is really difficult. You need like a Van Allen return cadence through the radiation belts is like once every 9 hours or once every 4.5 hours. So to tease out, you know, that kind of continental effect is tough. But the seasonal effect should be there. And we at UCLA, we had a former postdoc who looked at that, and you know, we couldn't really tease out the signal, the seasonal dependence. But it's probably due to the fact that there's others. It's tough to isolate just the lightning, right, when everything else is going on as well. And the lightning effect, you know, His is really important, you know, in that sort of same kind of L range as lightning and VLF. And so it's tough to disentangle them all.
And I mean, the electrons are sampling
Yes.
in a matter of 10 minutes,
Right.
the
whole environment.
right?
Yeah, exactly.
So you already average all the local times.
Yeah, well, the electrons are doing that averaging for you, right? The measurements of these electrons, you know, they're drifting around the Earth in an hour or less, and so they're sampling the entire wave environment. Yeah.
Should the LEO give you more?
Yes, so LEO does give you more information. There's additional challenges with doing this from LEO because you're only looking at the low pitch angle particles, right? You really, in order to, you know, you saw how the scattering rate is dependent on pitch angle, and so when you do it from LEO, you're only looking at a very narrow pitch angle range. Whereas with Van Allen probes, we see almost the entire angular distribution range. I mean, I could think up of a mission to propose to NASA that could make that measurement. You want to be in a higher LEO where you can see the trapped and the precipitating, and you can make some headway on that. But yeah, LEO has its own unique challenges. Hey, Stan, yeah.
You said the two things that caught my attention.
Uh-huh.
Is that the Earth is rotating underneath the radiation belts.
Right.
And that the electrons are drifting rapidly
Right.
around the Earth.
Right.
Presumably, therefore, sampling all the different.
Yes.
movements, I would call it.
Yep.
So doesn't that mean that they're sampling, they're drifting through different locations in the magnetic field where the field lines connect to different regions of
Yes.
atmosphere, ionosphere?
Mm-hmm.
So then doesn't that mean that they must, as they come into the places where the field lights connect to lower altitude,
Mhm.
the so-called south node,
Right.
if you
Yep.
use that terminology,
Yep.
that is what's dominating the loss as they come?
Yes, so at very, very low altitudes, that is what's dominating the loss. But at higher altitudes, particularly for the more equatorially mirroring particles, which is what we're measuring here with Van Allen probes, those effects aren't important because they're not mirroring all the way down in the atmosphere. I should have mentioned that at the beginning. You know, most of this plot was produced from particles that are mirroring very close to the magnetic equator at high altitude. So they're not sampling that. They're not subject to those low altitude mirror point effects.
And that's the bulk of the population because it's assigned to
So
the.
they have to make it slowly down to lower.
They get scattered in lower in pitch angle.
They slowly make it down to lower L shell.
Yeah.
And then once they reach that critical,
L shell and pitch angle.
Region.
Yep. Then they're ultimately lost.
then
Yep.
they're
Yep.
going to be lost.
Yep.
And lost in content by configuration, magnetic field,
Right.
other things. So can you use these information to estimate precipitation rates?
I mean, that's what these are, right? I mean, in some sense. That's something we're working on. We haven't gotten there yet, but you have to make a lot of assumptions about the population that's available for scattering. So, you know, that it all depends on what's trapped, right, out at high altitude. You can use this information about the scattering rates, but you have to know how the dynamics are changing, how the fluxes are changing at higher altitude to know what's ultimately coming down.
Okay, thanks again.
Okay, thank you.